Hi, I'm June with Nibbles and Bytes. In this third part of the VIC-II series, we're going to continue to talk about hardware sprites, sprite pointers, and sprite animations. Something I should mention about the coordinates used for sprites is that the documentation seems to talk about it in inconsistent ways. Both the diagrams used in the 128 Programmer's Reference Manual and computes mapping the 128 use different numbers. For the most part, we're going to have to puzzle out the coordinate system a little. In my experiments on this NTSC machine, the maximum Y value that is still visible is 249. As for the X, the max is 343, as you can see here. Note that the coordinates are different because of BASIC's tendency to start with 1 instead of 0 for indexes. This means that the machine language maximums are actually 1 less. Unfortunately, I don't have a PAL machine to compare with, so the only reference I have is the manuals, despite their bugs. For those of you using PAL machines, I've shown you basic commands that you can use to verify the coordinates with, so please check and let me know what you find in the comments below. Okay, let's get to the whiteboard and figure out how the VIC-II knows where our sprite shapes are in memory. It's a little confusing, but we'll figure it out. Remember that the 8502 can access either block of 64K segments of the 128's RAM. The VIC, on the other hand, can only access 8 total 16 kilobyte segments, 4 per 64 kilobyte block. This gives us 4 banks of 16 kilobytes each that must contain the text area, color RAM, sprite pointers, and sprites. Sprite animations can be done any number of ways, but the easiest is by cycling sprite pointers. The pointers are always located at the end of the text screen, regardless of where it's been placed in RAM. By default, they reside between 7F8 and 7FF. Below the text screen is all of the sprite shapes, starting at 800 and ending at FFF. This default area has enough room for all 8 sprites, but with a little creative work, with the MMU and video banks, you can store much more than this. The pointer area only has enough space for 8 sprite pointers. Each points to a location somewhere in the current video bank. Each of these pointers must point to a location that is a multiple of 64, since the shapes are 64 bytes long. We don't store the actual address, just the pre-multiplied value. Okay, let's play with these a bit. You can see in this memory dump all 8 sprite pointers. If we swap the pointers of sprite 0 and 1, our jailed sprite should pop out in front of the jail. This is because the lowered number sprites have higher priority and are drawn in front. Oh, sorry little convict. Let's fix that. Our convict got scrambled because the sprite multicolor bits are stored elsewhere. If we swap the bits in the multicolor control register, he'll become unscrambled. Then all we have to do is swap the colors in the sprites. And voila! Our convict is free! Okay, so now that we have a technique, we need some data. Let's start by drawing the first frame of a walking cycle. We'll do this in Sprite 3 first, and later copy it into the remaining sprites. Now that we have our first frame, let's use the monitor's transfer command to copy the frame around. The first parameter is the starting address to copy from. Sprite number 3 starts at E80 hex. The second is the ending address, inclusive, in this case, EBF hex. Finally, we provide the destination to transfer to. Do this 4 more times, and then we have our initial frames. Since we only copied the shape, their multicolor bit and colors are wrong, but that's easily fixed. All that's left for the data is to fine-tune the drawing and make his arms pump as he walks. The technique I'm using here mimics traditional animators' onion skinning and tracing. It's just a bit more awkward. So here's what the final cycle looks like. There's one repeated frame in the cycle so that our loop can be simplified to go in one direction instead of ping-ponging. Okay, now we have our sprites, but how the heck do we load and save them? Loading and saving in the monitor is only slightly harder than it is in BASIC. The save command starts the same, with the file name coming first and the drives coming second. Since we're working in machine language, the command needs 2 additional parameters, the start address and the exclusive end address to save. Loading, on the other hand, is actually easier than BASIC. All we have to do is use the file name and which drive to load from. The save command stores the starting address as the first 2 bytes of the file, so the load command knows right where to load it. If we check SPRDEF, we can see that we successfully saved our sprites. Okay, now that we have our sprites, let's animate them walking across the screen. To fine-tune our algorithm, let's write it in BASIC first. It's a simple straight-through loop with a slight delay added so that we can see the cycle. In this program, we're actually toggling sprites on and off in sequence, but it proves that the theory is sound. Unfortunately, BASIC doesn't have a way to cycle sprite pointers without using peek and poke commands. The program we wrote, though, does enough to verify our frames work. So let's move on to the real program. Our program is going to be very similar to the previous animation program. Because of its complexity, we're going to have to break it up into subroutines like we did before. The first subroutine is our initialization code. This sets up our initial state, similar to how we did in the previous episode. We set sprite positions, definitions, and disable the basic IRQ handler. The next subroutine swaps the jail with the convict so that he appears on top as though he broke out. Since BASIC initializes sprite 0 to point at location 38 and sprite 1 to location 39, we simply increment 0 and decrement 1 to swap them. Once we swap the pointers, we swap the bits in the multicolor register. And finally, swap the colors in the color registers. The next subroutine is our frame animation code. Each time this subroutine is called, we advance the frame in our animation by cycling the sprite pointer. First, we increment sprite 0's shape pointer by 1. Next, we load the pointer into A so that we can compare it to the pointer of the last frame that we want to use. If the pointer is less than 3e hex, we simply jump to the return instruction. Otherwise, we restart the cycle at our first frame of animation, located at 3a hex. The next routine is going to give our convict a little shudder as though he's fighting to get out. First, we set up our Y register for a loop by loading it with 255. Next, we increment sprite 1's X register by 1. We delay a little, decrement the same register by 1, delay some more, decrement Y, and if we've not yet reached 0, we start again. The following subroutine is our delay routine. This works exactly the same as the one we wrote in the previous episode by looping 255 times while reading a register. After the delay routine, we have our sprite MSB flipper routine. Again, it's exactly the same as the previous episode and simply inverts the MSB each time it's called. Lastly, we have our main routine. It's a little different this time around, and we'll break it up into 2 parts. The first part does a little initialization by setting sprite 0 and 1's pointers to their default values. We then call the shudder routine to make the convict seem like he's fighting through the bars. After he's done his magic, we swap the 2 pointers to make him appear on top of the jail. The second half of the routine is very similar to the original, with added animation. First, we delay. Next, we call the animate subroutine to increment our frame of animation. We delay some more, and then we increment sprite 0's X position to move him to the right. If we've rolled the register to 0, we flip the MSB and start all over again. Now that we have our program, let's give it a shot from BASIC. Remember that we have to run our program in bank 15, so we use the bank keyword to set that up. Once that's done, we can call our program using the sys keyword and our starting address of 1800 hex converted to decimal, or 6144. Yes! I mean, no, he broke out, but I mean, yes, it works. That was a lot of work. Let's save this stuff to disk. That way we don't have to work on this again. Saving our program works exactly the same way we saved our sprites earlier. File name, device, start, and end. Voila! Well, that about wraps it up for the VIC-II's hardware sprites. For the next and last video on the VIC-II, we need to cover backgrounds, which means editing the character set. Again, I'll have all the programs we used up on the website after I've posted this video. Please take a look and let me know if you run into any problems in the comments below. I'd also like to give a shout out to the first folks to sign up as my patrons: Claudia Bunsen, M. Folsom, Garth Howe, Sten Glolf, Lawrence Gonsalves, Robert Jefferson, Jay Holmes, Mike Windsor, and J.D. Robbins. Thank you all very much for your patronage. It means a great deal to me and keeps me going. If you'd like to join them in their patronage, you can find my Patreon page in the description below. And with that, thanks for watching, and see you in the next episode. I can't believe I'm doing this so many times. It's such a simple sentence.